dear students, I am Meghamala, working assistant professor from Electronics and Communication Department, Institute of Aeronautical Engineering. And here I am going to share something about the problem solving on gate level modeling. So here, as we discussed in the previous class of problem solving on the gate level modeling about the comparators, right? How to solve the problems by considering the comparator circuit. And now we will discuss about the decoders. So here, the decoder, 2 to 4 decoder, if you consider, basically what's a decoder? Decoder is nothing but n input, 2 power n output, right? So decoders are the binary decoders where the decoder has n input, n bit input lines and 2 power n output lines, and it can be 2 to 4 and 3 to 8, 4 to 16 line configuration. So here, these are the configurations that we can consider for it. And then the binary decoder can easily be constructed using basic logic gates, right? So basic logic gates, and then the very low code for 2 to 4 decoder is implemented by the structural and as well as the behavioral modeling. Now, we will see the truth table for this decoder. So 2 to 4 decoder, the truth table or its logical design goes with this. So here, encoder designing, decoder designing as 2 to 4, right? So these are the 2 inputs and these are the 4 outputs. So 2 to 4 inputs and as well as the output. And now if you observe the truth table, here I have the input A0, A1 and the output B0, B1, B2, B3, right? And then we will see the input as A0, B0, A0, 0, 0, 1, 1, 0 and 1, 1. Now we will see when both inputs are 0, what happens is my output B0 will, the condition, the output, the LED of B0 will glow, right? So the B0 will be in the on state. The rest of will be in the off state. Then when the input A0 and output A1, when the input A1 as 0, output one more input as 1, then we see the B1 as in the on state and the rest of will be in the off state. So similarly, if both the inputs are 1, 1, then what happens is the B3 output will be in the on state, then the remaining will be in the off state. Then similarly to the encoder, we can also go for the 2 to 4 decoder. Okay, how this is about the 2 to 4 decoder, right? Encoder is quite opposite to the decoder. So here we have 2 to 4 decoder, then we can construct the 4 by 2 encoder as well, right? The mechanism will be different. So by here in the Verilog, by using the case statement and using if else statement and using logic gates, etc., we can easily draw, or else we can easily implement the decoder as well, right? So by using case statement, we can write down this logic, or else we can write down the code. And by using the if else statement also, we can write down the code. And also using the logic gates as well, we can easily write down the code. Okay, based on though it is decoder or though it is encoder, we can easily draw the circuit. Then, however, we provide example code for all 3 modules methods for better understanding of the language. So now we will see this is about the 2 to 4 decoder, and the syntax or else the code goes like this: module, the test bench, registers, X, Y and enable bits, and then via the connection purpose, we have the A, B, C, D are for the connection purpose, A, B, C, D and the integer I. And now here, as I said you, with the help of few if else statements, see here, with the help of case statements and using the if else statements and using logic gates as well, we can decode, or else we can code the structure, or else we can code the different module. And now we will see the integer I, the decoder 2 by 4 decoder. So here the decoder is 2 by 4, as we know that 2 input and 4 output, right? So here 2 input, 4 output. Based on that, X, Y enable. Based on the enable bit, we can able to get the output based on it. And then now we will start in the code, we will start the initial begin. So in the initial begin, X, Y and enable. Based on the enable bit, the output is to be considered. Okay, whichever it is. Sometimes it is B0 will be in the on state and the rest of will be in the off state. Sometimes B1 will be on state, the rest of will be off state. B2 on state, the rest will be off state. B3 on state and the rest will be off state. And then monitor the enable. If the enable is 1, okay, if the enable is 1, the condition by using the for loop, we can say that I is equals to 0, I less than 10 and then I plus plus begin. And then what am I doing is, with that 1 nanoseconds of delay, here I am writing the my output is being enabled as X and Y. Okay, randomly my output is being enabled X and Y. So here how randomly is, for example, see, when both are 0, what happens is my B0 will be in the on condition, right? The B0 will be in the on condition and rest all the gates will be in the off state. And then when when one of the input is in 1, then what happens is B1 will be in the on conditions and the other gates will be in the off state. Okay, so that's how I'm writing my code. Then N module and finally N module. So this is how the 2x4 decoder, the what do we say, 2x4 decoder coding part can be written with the help of if-else statement. We can write this code in terms of case statement, and also we can write this statement in terms of if-else statement as well, right? Then after writing the code, the second thing is we have to draw the circuit diagram and as well as a truth table. And from the truth table we can get the expressions, right? So this is a truth table, and from the truth table we can get the expression, and this is the circuit diagram. So in the circuit diagram, this circuit diagram can be drawn with the help of this one. See, the input and the output. See, for example, A0, A1. Okay, this is A0 bar, and here it is A1 bar. Okay, finally, what is a D0? D0 is nothing but it is a combination of A0 and it's a combination of A0 and A1, right? So that is D1, and this is nothing but A0 bar, A0 bar and A1 bar, and here it is A0 bar and as well A0 bar and as well what is this, A1, and here it is A1 bar, and one more thing is A0 bar. So here I can say that 0 0 0 1 1 0 and 1 1. So this is all about 0 0 0 1 1 0 and 1 1. So when the condition it is 0 0, then when it is 0 0, we say that the D0 will be in the on conditions, right? When the statement, when the condition is about 0 1, if it is 0 1, then the D0 will be in the on condition. When if it is 0 1, and then D1 will be in the on conditions, and 0 0 0 1, then coming to 1 1 0, and if it is my inputs are 1 0, then the D2 will be in the on conditions. When my inputs are 1 1, right? So when my inputs are 1 1, and D3 will be in the on state. So remember that if it is in the on state, if D0 will be in the on state, okay, if D0 will be in the on state, then D1, D2, D3 will be in the off state. Similarly, if D1 will be in the on state, similarly D0, D2, D3 will be in the off state. Like that. That is how the truth table can be drawn. And from the truth table, the ultimate thing that we have to we will do is writing the expressions. So the expressions are nothing but in terms of minterms and as well as the maxterms. So D0 is 1, right? So what is D0? D0 is all about A1 and A0, isn't it? D0 is A1 bar and A0, and then D1. When the D1 is on, when A1 bar and A0. Okay, A1 bar and A0, and then A1 A0 bar, then A1 A0. So here you can observe one thing is A0 bar 0 0 0 1 1 0 and 1 1. So these are the conditions. Based on the conditions, the enabling of the output, okay, decoder output is observed. D0, D1, D2 and as well as D3. Okay, that is how we can draw the we can write the expression. So likewise, when it comes to the 4x2 encoder, so the 4x2 encoder mechanism is also the same thing, but here it is called the 4-bit priority encoder. So why we are saying it's a priority encoder? The priority of the bits can be calculated based on the input that you are considering. So this is a priority bit encoder. So as we have 4 bits as 4 as input and 2 as the output, right? So 2 as the output, that is 2 power n input is n output, right? So this is a encoder. So what is a decoder? N input, 2 power n output. and the third output way is considered in the valid indicator. So here if you observe D0 to D3, so D0 to D3, these are the four inputs, and A, B, C, these are the 4x2 encoder, right? So A, B are the inputs. So if you observe, when both are 0, 0, when both are 0, 0, what happens is D3 is in on state, and when one is when both 0 and 1, and then we see the D2 is in the on state, and if it is 1, 0, and D1 will be in the on state. If it is 1, 1, and D0 will be in the on state. So this is quite opposite to the decoder. So encoders are quite opposite to the decoder, but the same mechanism can be is applied, where then in the decoder you have two inputs. If you have two inputs, four outputs, right? But whereas in the encoder you have four inputs to output as well. And now in the truth table we see that all the inputs D3 to D9 are the inputs, A and B are the outputs, and one more bit we have is the valid indicator. Indicators are nothing but they just indicate if if A and B, with respect to my inputs A and B, my bit D0 is in the on state. So my indicator will indicate that D0 is in the on state, like that. And then here D3 is input with the highest priority, and D0 in the input with the lowest priority. So obviously here, see, this is D0. D3 is the highest priority. Why is the highest priority? Why? Because it is 1. And the rest of all the inputs are all the inputs are in 0. It means what they are obviously lowest priority. 1 is nothing but the highest priority, and 0 is nothing but the lowest priority, right? Then finally, if D3 input is active low, what happens is the next priority output will be in the active state. So if you observe here, first as per this input, the first priority state goes to D3. And then immediately when D3 is in the highest priority, for the next combination, D2 will get the highest priority. And after the D2 is getting the highest priority, and then immediately based on the condition, D2 will get the highest priority. And then after D2, D1 get the highest priority. So likewise, the switching of the priorities, highest priorities will vary from the first bit to the last bit. And then if the input D3, D2 are active low, what happens is D1 has the highest priority. When D3, D2 are in the active low or in the lowest priority, obviously D1 will be the highest priority. Then the output expressions can be told in 4-bit encoder with the help of what? Karnaugh maps. Using the Karnaugh maps, we can easily, we can easily identify, or else we can easily reduce the number of gates here. So these are the K maps. So the K maps are observed with respect to the truth table. With respect to the truth table. So this is the truth table based on B, and this is truth table based on A. So the K maps, the simplified expressions of the output A and B are like this. See, these are the simplified expressions, outputs of A and B, right? Then the circuit diagram of 422 decoder priority encoder. From these outputs, expressions is displayed through logical gates below. So from these Karnaugh maps, what am I telling is we can easily draw the circuit diagram. So this is a circuit diagram which is observed, or else which is observed from with respect to the Karnaugh maps, the expressions from the K maps, K map expression. So before going to the last state of this encoder, we will see the code. In the Verilog code, how can we write this Verilog code? Is module, the name of the module is a keyword, and then followed with the name of the circuit that you are considering, and my circuit is encoder 4x2, and in the port list I am declaring my input, output, and as well as the in-out port, right? So input are D0 to D3, and output ports are A0 and as well A1. Then what am I doing is, in order to connect all these components, input with respect to the outputs, I am using a wire X, Y, Z indicated, declared, and then NOT gate. So what sort of gates are you using here? So in the expression, in the circuit diagram, if you observe here, we have used AND gate, and we have used OR gate, and also the NOT gate. So for what purpose you are using all these things, we have to mention, or else the declaring of the gates are mandatory. Then now see here, NOT gate is meant for X and D2, and AND gate is meant for Y, X and D1, and then OR gate is meant for AY and D3 as well, and one more OR gate is meant for A1, D2 and D3. So after declaring all the gates, okay, all the gates with respect to the connectors, then finally we are ending up with the keyword and module. So start your code with the module, keyword, and then finally end with your code with the key module, keyword and module, and then followed with the test bench. In the test bench code, what we see is initialize all the inputs. Okay, initialize. How are we initializing? If D0 is equals to 0, then D0 is equals to 1. If D0 is equals to 1, then D1, D2, D3 are in the off state. Obviously, if D1 is 1, then D0, D2, D3 will be off state. And obviously, when D2 is 1, then D0, D1 and D3 will be off state. And the final one, when D3 is 1, D0, D1, D2 will be in the off state. Okay, so that is how we represent here in the test bench each and everything with 100 nanoseconds of delay. With 100 of delay, we are mentioning all these things. Okay, right, then finally ending up with the keyword and here ending up with the keyword and. Why? Because here we have started with begin, right? So we have to end it with the end. Then finally coming to the applications of priority encoder. So here, before going for the applications, if you observe here, this is a circuit diagram, structural modeling. This structural modeling we have got it from the truth table, and the truth table is the structural modeling is observed from the Karnaugh maps, and the Karnaugh maps are observed from the truth tables. Right? They are all these things are interrelated, interconnected to each other. So the structural modeling of this 4x2 encoder is all the 4 inputs and the 2 outputs is observed this is drawn with the help of the gates that you are considering based on the expressions from the Karnaugh map. And then coming to the encoders application. So where can we use this encoders is it reduces the number of wires and connections needed for electronic circuits designing with multiple input line keypads and keyboards. So remember that the applications or the advantages of this encoder is what it does is the number of wires and connections are in the circuit with multiple inputs and outputs. It reduces the number of connections. Obviously, if you connect, if you are designing some module and if you have a connections where it all becomes like a messy, then it's obviously the output is observed with the delay, and also the proper output is not observed, right? Interruptions may occur due to the bad interconnections. So in order to avoid that bad interconnections, we can better go with the encoder. So what is an encoder does is it just reduces the number of wires and the connections. The number of wires and connections can be easily reduced. In order to the multiple input lines can be considered with a single input lines. That's how we can reduce the connections and the wires. And then also it used to control the positions in the ship's navigations and the location of robot arm. So so these are the 2 specific applications where we can use this encoder. So here we saying that in the ship navigation and also in the purpose of the robot arm, the location of the robot arm, the encoders plays a vital role. Okay, and then goes with the it used to acquire highest priority inputs in various microprocessor interrupt control systems applications. So in various microprocess applications, we see that the highest priority inputs, sometimes being a designer, we are unable to give the priorities, right? So based on the inputs, though the inputs are, some inputs may have 1 and some inputs were in the low state condition. So in such scenario, we'll feel some difficult in order to give the priority. Right, so by using this priority encoders, 4x2 encoders or 3x decoders, we see that we can easily prioritize. We can easily prioritize the inputs. The considerations can be easily prioritized. Right, then it protects the entire network from hackers by transmitting binary code to the network. So one of the most important applications that we can consider through this encoder is it protects the entire network from hackers by transmitting binary code to network. So by transmitting the code, giving code to the network, we can easily find out, or else we can easily spot the hackers. We can easily spot the hackers. Okay, then it is used to adjust the speed of industrial motors. It is used in robotic vehicles. So one more applications of this encoders is we can use in the industrial motors. Okay, we can use the speed of the motors can be reduced or they can be controlled using these encoders. And one more example is in the robotic vehicles, we can use this encoders. So these are the few applications of the encoders. And also remember that by using this this Cornung maps, one more time, by using this Cornung maps, we can able to reduce the complexity of the circuit. Okay, the number of gates can be reduced. And also the circuit that you are considering, there are many various applications where that particular circuit can be make use in the real times as well. So obviously, if you observe these applications, we are saying that in the navigation, in the ship navigation, and as well as from the hackers, okay, from the hackers, and also in the robotic vehicles, and also for the industrial motors, these encoders are playing a very vital role. So and also not only the encoders, whatever the circuit that you're considering, whatever the digital module that you're considering, always remember that reducing the number of gates always gives you a greater output. Okay, a greater output can be achieved in you if you reduce the minimal number of the gates. Okay, and also in the previous example, we have come across the comparators as well. So in the comparators also, whatever the based on the inputs, the comparators, 2-bit comparators or 4-bit comparators, what sort of inputs that you're considering, make sure that the circuit should be reduced. The complexity of the circuit can be reduced with the help of minimizing the gates. How can we minimize the gates? Is by using the Cornung maps. We can easily minimize the gates, and the connections which are needed can be easily considered, or else the connections, the variables and the parameters can be easily considered from the Verilog primitives as well. Okay, always remember that if you are drawing, or if you are building some basic building blocks, you have to keep it in your mind that the complexity, okay, the complexity of the circuit should be reduced. In order that for that you have to go with the circuit diagram, and then followed with the truth table, and from the truth table reduce the Cornung maps, use the Cornung maps, get the Boolean expressions, and from the Boolean expressions you can able to draw the circuit diagram based on the gates. Okay, based on the gates. Okay, this is how the procedure goes on. So this is a small example. See, in the circuit diagram, if you observe, it's a 2 to 4 decoders. You have a 2 to 4 line single bit decoder. So this is a single bit decoder. A0 and A1 are the 2 inputs, and D0 to D1 are the 4 outputs. Okay, based on the input selection lines, we can able to say that which output is in the on condition, and if one output is in the on condition, the rest of all the outputs will be in the off state. Okay, this is how the mechanism of the encoders and decoders goes on. Not only the encoders but also the comparators. Okay, but also the comparators and as well as the multiplexers. So multiplexers, comparators, demultiplexers, encoders, decoders. Okay, all these major blocks we can able to easily get the output with respect to the circuit diagram that you are considering from the truth table, and then follow the Cornung maps, and then the expressions, and then finally the circuit diagram. Okay, so this is all about the 2 to 4 decoder, and there how we can solve easily the problem pertaining to the connection. We can easily solve the problem pertaining to the routing. We can easily solve the problem pertaining to the placement, and also we can easily solve the problem pertaining to the floor planning as well. Okay, so this is a small example based on the gate level modeling. I hope you all got the point. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.